Ever wondered what makes your gadgets smarter and your devices last longer? It all comes down to a silent superhero: dielectric materials. Alternate opening, exposing the hidden force inside your electronics. Dielectric materials. They don't just sit there, they shape every piece of modern tech. Let's find out how. Before smartphones or energy-saving lights, we needed special materials to manage electricity safely. Dielectric materials are the unsung heroes. They store energy, protect circuits, and keep your devices running smoothly. But here's the catch. Old-school polymers are flexible but weak, while ceramics are tough but too rigid and expensive. So, can we get the best of both worlds? Scientists are now mixing biopolymers with nanoparticles and even using gamma radiation to unlock new properties. By tweaking these materials at the tiniest scale, they create dielectrics that are flexible, powerful, and eco-friendly. It's not just chemistry. It's physics, materials science, and a dash of radiation magic. That's how dielectric materials are shaping the future of technology. Stick around to learn more, right here on For Science Salah Lotfy channel.
Welcome to For Science Salah Lotfy channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Salah Lotfy channel. العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Why do 90% of new electronic materials rely on advanced nanocomposites? What happens when scientists zap them with gamma rays? Let's decode the latest research findings together. Scientists are pushing the boundaries of materials science by combining ZrCeO4 nanoparticles with chitosan to create high-tech nanocomposites. But here's the twist. These materials were exposed to gamma rays, a form of high-energy radiation, to see how their structure and properties change. This research was conducted by an international team of scientists: Professor Dr. Emad Ahmed, Associate Professor Dr. Sultan Al-Sufyani, and Associate Professor Dr. Shurug Al-Thaqafi from the Department of Physics, College of Science, Taif University, Taif, Saudi Arabia, along with Professor Dr. Ahmed Ashur from the Materials Science Lab, Radiation Physics Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Published in the Journal of Materials Science, Materials and Electronics in 2025, this groundbreaking research reveals a direct link between how these nanocomposites are built and how they perform after irradiation. The team, based in Saudi Arabia and Egypt, found that gamma ray treatment can tune the material's electrical, optical, and mechanical properties, potentially opening doors for advanced sensors and electronic devices. So next time you think about the future of electronics, remember sometimes a little radiation can spark a big leap in technology. Stay tuned for more scientific insights, only on For Science Salah Lotfy channel.
Hey everyone. Today, I'm diving into a question that's lighting up labs around the world. Can we supercharge natural biopolymers into electrical powerhouses using the wild world of gamma irradiation and metal oxide nanoparticles? Let's start at square one. Dielectric materials. If you've ever used a capacitor, you've seen these in action. Dielectrics are materials that don't conduct electricity, but they're champs at storing electric charge. They're the unsung heroes in everything from your phone circuits to cutting-edge medical devices. But here's the catch. Most of our standard dielectrics are made from conventional polymers like PET or PVC. They're cheap, flexible, and reliable, but they come with problems. They're often non-biodegradable, have limited performance at high temperatures, and their environmental impact. Not great. That's where biopolymers slide into the spotlight. So, why are biopolymers making scientists so excited? Well, these are natural polymers. Think cellulose, chitosan, even starch, that are renewable and biodegradable. Imagine using materials from plants, crustacean shells, or even food waste to store energy or insulate electronics. But raw biopolymers aren't perfect substitutes. On their own, they don't always measure up to synthetics when it comes to dielectric strength or stability. Which brings us to the big question. How can we make biopolymers into true competitors, or even superstars, among dielectrics? Here's where things get really interesting. Researchers are turning to gamma irradiation, a high-energy process that can actually change a polymer's molecular structure. Think of gamma rays as tools to snip, rearrange, or even fuse together the polymer chains at the atomic level. This can make the biopolymer tougher, more stable, and, crucially, much better at storing charge. But wait, there's more. Scientists are also adding metal oxide nanoparticles, tiny engineered particles of things like zinc oxide or titanium dioxide, into the biopolymer mix. These nanoparticles can dramatically boost the dielectric properties, helping the material resist breakdown and pack in even more energy. So the research question I'm chasing is this: by combining gamma irradiation and metal oxide nanoparticles, can we turn humble, eco-friendly biopolymers into high-performance dielectric materials that rival, or even beat, synthetic plastics? Stick around, because in the next episode I'll break down how these experiments are done and what the results could mean for everything from green electronics to sustainable energy storage. Science is just getting started on this one, and if you're passionate about science and want to keep up with the latest discoveries, don't forget to subscribe to the For Science Salah Lotfy channel.
Imagine the tough shell of a shrimp or crab, made from chitin, a natural polymer. Treat chitin chemically, and you get chitosan, a biodegradable, biocompatible material that works in harmony with living systems. Chitosan is used for everything from wound healing to water filtration. Now, meet polyvinyl alcohol, or PVA, a synthetic polymer found in laundry pod films. PVA forms strong, clear sheets and dissolves in water, making it versatile, but also limiting its use in wet environments. Both chitosan and PVA are long-chain polymers, but each has weaknesses. Chitosan can be brittle, and PVA dissolves in water. Scientists blend them to combine chitosan's antibacterial properties with PVA's film-forming strength. Their chains intertwine, held together by hydrogen bonds, creating a new material that's better than either alone. But challenges remain. Chitosan's fragility and PVA's water solubility limit their applications. To make a truly robust material for things like medical implants or advanced filters, these limitations must be overcome. That's where the next innovation comes in. By enhancing this blend, scientists aim to create a material that's strong, stable, and reliable. The solution? Reinforcement at the nanoscale. Let's see how nanoparticles change the game. The journey to a new material begins here. If you're fascinated by the science behind these innovations, don't forget to subscribe to the For Science Salah Lotfy channel for more discoveries and deep dives into the world of materials science. To strengthen the chitosan PVA blend, scientists add nanoparticles, specifically zirconium cerium oxide, Zircon-04. These microscopic particles act like rebar in concrete, reinforcing the polymer matrix. Their huge surface area lets polymer chains anchor tightly, creating a tough, interconnected network. Zircon-04 brings more than strength. Zirconium oxide adds toughness and heat resistance, while cerium oxide protects against degradation. Together, they make the material resilient to stress, heat, and chemicals. The result is a composite, no longer just two polymers, but a new material with distributed strength. Nanoparticles block cracks and distribute force, preventing failure. This approach is used in everything from carbon fiber bikes to spacecraft shields. By embedding these tiny reinforcements, the material becomes far more than the sum of its parts. But scientists don't stop there. They have one more trick to make it even better. To further enhance the material, scientists use gamma irradiation, a powerful energy source. Gamma rays trigger cross-linking, bonding the polymer chains into a strong, three-dimensional network. This process transforms the blend from a fragile film into a robust, water-insoluble sheet. Cross-linking solves PVA's biggest flaw. It no longer dissolves in water, only swells like a sponge. The Zircon-04 nanoparticles help focus the radiation, accelerating cross-linking and strengthening the interface. The result is a tightly bonded composite, with every component locked in place. Gamma rays and nanoparticles work together, creating zones of dense networking and superior stability. The material is now tough, stable, and ready for demanding environments. This synergy is the secret to advanced high-performance composites. But how do these steps come together to create something truly new? This is dual modification, combining nanoparticle reinforcement and gamma-induced cross-linking. Nanoparticles provide a rigid framework. Cross-linking ties everything together. The result? A material that's tough, stable, and customizable for specific needs. Scientists can fine-tune flexibility, swelling, and strength for applications from medical scaffolds to water filters. This process unlocks the hidden potential of everyday materials. By engineering at the molecular level, we create solutions for a stronger, healthier, and more sustainable future. From shrimp shells and laundry films to high-tech composites, this is the power of materials science. The future is built from the smallest building blocks, transformed by creativity and innovation.
What makes materials strong, flexible, or tough? It's all about what they're made of, and how we can make them better. Scientists mix polymers, long chains of molecules, with nanoparticles, which are thousands of times thinner than a human hair. When combined, these create nanocomposites, materials engineered from the inside out for new abilities. The polymer provides a lightweight, moldable base, while nanoparticles add strength, conductivity, or heat resistance. For example, adding the right nanoparticles can make plastic as strong as metal, but much lighter. This could transform industries, from aerospace to sports equipment. But how do we know what's happening inside these materials? We need special tools to see the invisible. These tools reveal how nanoparticles change the polymer's structure and properties. Understanding this is key to unlocking the full potential of supermaterials. Science lets us design materials for the future, one molecule at a time. If you enjoyed this video, don't forget to subscribe to the For Science Salah Lotfy channel for more fascinating science discoveries. To see how nanoparticles and polymers interact, scientists use FTIR, Fourier Transform Infrared Spectroscopy. Molecules vibrate in unique ways, and FTIR shines infrared light to reveal their dance moves. Each material has a distinct vibration pattern, a molecular fingerprint. When nanoparticles and polymers are mixed, FTIR shows if they're truly interacting. Shifts in the vibration pattern mean the polymer and nanoparticles are connected, like a molecular handshake. This connection is crucial. It means nanoparticles are bonded to the polymer, not just floating around. Strong handshakes let nanoparticles transfer their properties to the whole material. When stressed, the polymer and nanoparticles work together as a team. FTIR proves this teamwork is happening at the molecular level. It's chemistry in action, building stronger nanocomposites. Next, we check how nanoparticles affect the order of polymer chains using X-ray diffraction, or XRD. Polymers have both neat crystalline regions and messy amorphous ones. XRD shoots X-rays at the material. Sharp peaks mean order, broad humps mean disorder. Adding nanoparticles often disrupts the neat packing, making the material less crystalline. This can make the material more flexible or less brittle. Nanoparticles tune the internal structure, changing how the material behaves. By controlling nanoparticle content, we control the material's order and properties. XRD gives us a direct look at these changes. It's a clear example of nanoscale cause and effect. To see how nanoparticles are spread out, we use a scanning electron microscope, or SM. SEM images show if nanoparticles are evenly dispersed or clumped together. Good dispersion means a stronger, more uniform material. Like chocolate chips spread evenly in cookie dough. Clumps create weak spots, but even distribution strengthens the whole material. SEM also reveals changes in surface texture and density after adding nanoparticles. Nanoparticles fill gaps between polymer chains, making the material denser and tougher. Looking at fracture surfaces, a rougher texture means it took more energy to break, proof of increased toughness. SEM gives us visual evidence of how nanoparticles improve the material. It's like seeing the recipe's success up close. Nanotechnology is all about getting the mix just right. All these tools, FTIR, XRD, SEM, help us connect a material's structure to its properties. Structure determines strength, flexibility, and more. Think of it like Lego bricks. How you arrange them changes what you build. In nanocomposites, the arrangement of polymer chains and nanoparticles is key. FTIR shows chemical bonds, XRD reveals order, SEM displays particle layout. By piecing together these clues, we predict and design material performance. Strong bonds and good dispersion mean toughness. Disrupted order can mean flexibility. Understanding structure-property relationships lets us engineer materials for any need. This turns material science from guesswork into precision design. It's how we build a better world, one molecule at a time. Hey science fans! Today, let's talk polymers. Long chains made of repeating units like a beaded necklace. Our focus, CSPVA, a blend of chitosan from shrimp shells and synthetic polyvinyl alcohol. Mix them and you get a useful material. But it has a weakness: heat. When heated, the polymer chains vibrate more, straining and eventually breaking their chemical bonds. This is called thermal degradation. The material doesn't just melt, it breaks down at a molecular level. The result? The polymer becomes brittle, changes color, or releases gases as it falls apart. That's a big problem for electronics or energy devices, where heat is everywhere. The challenge: how do we keep these chains from moving so much when heated? Without anything to hold them, the chains are free to vibrate and break. The more they move, the more likely they'll snap. To make these polymers reliable, we need to anchor the chains and limit their movement. The puzzle: how do you reinforce something so tiny that it stands up to heat in the real world? Let's find out. And if you're enjoying this journey into science, don't forget to subscribe to the 4Science Salah Lotfy channel for more fascinating discoveries. The solution? Nanoparticles, specifically zirconium cerium oxide, ZrCeO4. These particles are thousands of times smaller than a human hair. When mixed into CSPVA, they interact with the polymer chains, acting like microscopic anchors. Through hydrogen bonding, the nanoparticles form a network of connections with the chains. This web makes the structure more rigid and stable. Now, when heat is applied, the chains can't wiggle freely. The nanoparticles hold them in place. The result: the polymer can withstand much higher temperatures before breaking down. Think of the nanoparticles as extra support cables on a shaky bridge. They stabilize everything. By reinforcing the polymer from the inside, we create a material far more resistant to heat. That's the power of nanoscale engineering. Why is restricting chain movement so important? In regular polymers, chains move like spaghetti, easy to slide and wiggle. Heat just makes them move more, stressing and breaking bonds. ZrCeO4 nanoparticles act as crosslinks, tying the chains down at multiple points. This creates a rigid internal structure, dampening the destructive vibrations from heat. The chains can't build up enough force to snap their bonds. It's like trying to swing a rope that's tied down in several places. It barely moves. The result: the material absorbs more heat before breaking down. We trade some flexibility for a huge gain in thermal resilience. The nanoparticles create an internal scaffold, holding everything together at high temperatures. Reducing chain mobility is the secret to high-performance, heat-resistant polymers. That's how nanoscale control leads to powerful new materials. So, why does this matter? Electronics, phones, laptops, TVs, all generate heat, and their components need to survive it. Our CSPVA ZrCeO4 composite could make more durable insulators and circuit boards. For example, as a dielectric in capacitors, it can handle heat without failing. In energy storage, it's even more exciting. Solid-state batteries need stable, safe materials. Our composite's thermal stability means safer, longer-lasting batteries and supercapacitors. It could also enable flexible, wearable electronics, devices that bend but don't break down from heat. By making polymers that resist heat, we unlock new possibilities for technology. From safer batteries to bendable gadgets, controlling heat response is key to innovation. The future of tech depends on materials that can take the heat. That's why this matters. To wrap up, polymers like CSPVA break down when hot, limiting their use. The fix? Add ZrCeO4 nanoparticles, which anchor the chains and stop destructive vibrations. This simple nanoscale tweak makes the material much more heat-resistant. The result? Tougher electronics, safer batteries, and new tech possibilities. Nanotechnology shows that small changes can have huge impacts. By controlling materials at the molecular level, we solve big engineering challenges. The tiniest particles can make the biggest difference. That's the power of science and innovation. Let's jump into material science. Imagine materials like plastic or glass. Unlike copper, they don't conduct electricity, but they're great at storing electrical energy. When you apply an electric field, these insulators, called dielectrics, act like sponges for electrical energy. The key measure here is the dielectric constant, or epsilon prime. It tells us how much energy a material can store compared to empty space. A high dielectric constant means the material stores more energy, just like a superabsorbent sponge. But storing energy isn't perfect. Some is lost as heat, measured by dielectric loss, or epsilon double prime. That's why your phone charger gets warm energy loss in action. Ideally, we want materials with a high dielectric constant and low dielectric loss for efficient electronics. These two properties, how much energy is stored and how much is lost, are crucial for modern technology. Engineers are always searching for that perfect balance. Understanding these properties is the first step to mastering how materials behave in our electrical world. It's the science behind everything from capacitors to power grids. Dielectric properties are everywhere, powering the devices we use every day. Let's see how these properties change when we shake things up. If you're enjoying this deep dive into science, don't forget to subscribe to the For Science Salah Lotfy channel for more fascinating discoveries. Electric fields in electronics flip back and forth rapidly. This is called frequency. At low frequencies, the dipoles inside a dielectric can easily align with the field, storing lots of energy. But as frequency increases, these dipoles struggle to keep up, so the dielectric constant drops. Imagine a crowd trying to turn with a slow beat. Easy. But at a fast beat, they can't keep up. At low frequencies, energy loss can be high due to friction between moving particles. As frequency rises, there's a point where energy loss peaks. Maximum chaos. Beyond that, at very high frequencies, the dipoles barely move, so both energy storage and loss decrease. This frequency dance is key to designing circuits and components. The way a material responds to different frequencies determines its usefulness in electronics. Engineers use this knowledge to pick the right materials for each job. The interplay between frequency, energy storage, and loss is at the heart of modern electronics. Understanding this helps us build faster, more efficient devices. Now let's see what happens when we add a powerful force: gamma rays. Enter gamma rays, high-energy light that can blast through materials and shake up their structure. When a dielectric is exposed to gamma rays, its internal structure gets scrambled. Chains break, new bonds form, and defects appear. Scientists control the amount of change by adjusting the radiation dose, measured in kilograys. A dose of 15 kilograys is a sweet spot, enough to create big changes without destroying the material. This dose can dramatically alter dielectric properties. Broken chains and new charged particles, called free radicals, make the material respond differently to electric fields. It's like adding new dancers to our crowd, each with unique moves. The result? The material's ability to store and lose energy is transformed. Let's see how this plays out in the dielectric constant. After a 15 kilogray dose of gamma rays, the dielectric constant at low frequencies jumps dramatically. The material becomes a supercharged energy sponge. Why? Gamma rays break long molecular chains into smaller, more mobile segments. These segments move and rotate more easily, boosting energy storage. Radiation also creates more free charge carriers, which pile up at boundaries. This is interfacial polarization. The effect is strongest at low frequencies, where these mobile parts have time to respond. At higher frequencies, the effect fades as the segments can't keep up. This molecular-level control lets us engineer materials for better capacitors and electronics. Supercharged dielectrics means smaller, more powerful devices. It's a game-changer for technology. But gamma rays don't just boost energy storage, they also shake up how energy is lost. In material science, relaxation is how quickly dipoles return to normal after the electric field is off. Before irradiation, the material's relaxation is set by its original structure. Gamma rays break chains, creating smaller, more mobile segments with new relaxation behaviors. These new segments respond at different frequencies, shifting or adding peaks in dielectric loss. It's like teaching the crowd new dance moves. Suddenly the rhythm changes. By studying these shifts, scientists can see exactly how radiation changed the material. More mobile segments mean more ways to lose energy, explaining the changes in dielectric loss. Radiation rewrites the material's internal dance card. Activation energy is the push needed to get molecular segments moving. Before irradiation, long chains are like heavy rocks, hard to move, requiring lots of energy. Gamma rays break these into smaller pieces, lowering the activation energy. Now, it's like pushing pebbles instead of boulders, much easier. Lower activation energy means dipoles and charges move more easily and quickly. This explains the jump in dielectric constant and the changes in loss. Scientists measure this drop to see how much the material has loosened up. The easier movement of molecules is a direct result of radiation damage. This makes the material more responsive to electric fields. It's a key reason why gamma-irradiated materials behave so differently. So, why does all this matter? By controlling dielectric properties with gamma rays, we can design smarter, more efficient materials. High dielectric constants mean better capacitors, leading to smaller, more powerful electronics. This could revolutionize everything from smartphones to medical devices and energy storage. It's also vital for tech in harsh environments, like satellites or nuclear reactors, where radiation is a constant threat. Understanding these effects lets us build electronics that last longer and work better under extreme conditions. This research pushes the boundaries of science, helping us model and improve materials at the atomic level. The knowledge gained applies to fields from medicine to advanced plastics. Dielectric properties and gamma rays aren't just abstract science, they're the foundation for tomorrow's technology. By mastering these changes, we unlock new possibilities for innovation. And that's the real power of materials science. When I think about why Chitosan nanocomposites are getting so much attention, I have to start with the science. These materials aren't just another tweak on old formulas, they're fundamentally changing what's possible in multiple fields. Let me break it down. First off, Chitosan itself is a biopolymer, derived from chitin, which you find in the shells of crustaceans. By embedding nanoparticles into this already eco-friendly material, I'm seeing entirely new properties emerge. Improved dielectric strength, higher thermal stability, and even better mechanical flexibility. Compared to earlier chitosan-based nanocomposites, the latest generations show much more reliable performance. For example, the dispersion of nanoparticles is more uniform now, which means fewer weak points for failure. But how do these stack up against conventional dielectric materials, like silicon-based or petroleum-derived polymers? Well, here's the thing. Those traditional dielectrics often come with environmental baggage and can be expensive to produce or recycle. Chitosan nanocomposites, on the other hand, are not only biodegradable, but their starting materials are abundant and renewable. I'm talking about reduced dependence on fossil fuels, less electronic waste, and a much smaller carbon footprint. From a technical perspective, these composites offer a remarkable balance between high electrical insulation and flexibility. That's a big deal for flexible electronics, wearable sensors, and even next-generation batteries. Traditional dielectrics can be stiff or brittle, which limits how you use them. With Chitosan nanocomposites, I'm seeing devices that can bend, stretch, and still perform consistently. And let's talk economics. Chitosan is relatively cheap to source, since it's often a byproduct of the seafood industry. Combine that with scalable processing methods, and you get a material that's cost competitive, even for large-scale manufacturing. That's why I think these nanocomposites are a real game changer. They check so many boxes: performance, sustainability, and affordability. To sum it up, the scientific breakthroughs here aren't just about achieving better numbers in the lab. They're about creating materials that could reshape industries, all while being kinder to the planet and more accessible for manufacturers. That's what makes this so exciting for researchers and technologists alike.
Alright, let's wrap things up and take a moment to imagine what's coming next in the world of science and technology. As the sun rises on a new era, let's look ahead to the future. The pace of innovation is only accelerating, and every day brings us closer to breakthroughs that once seemed impossible. So, what have I uncovered about tomorrow's tech? The answers are as exciting as they are surprising. First, flexible electronics are changing the game. Imagine devices that bend, stretch, and even heal themselves. These aren't just science fiction anymore, they're being developed in labs right now. This isn't just cool, it's about bringing advanced tech to places and people where rigid devices just don't work. Think about remote villages, disaster zones, or even wearable health monitors that need to move with your body. Next, energy storage. The dream of batteries that last longer, charge faster, and are way safer is a massive scientific challenge. but researchers are making real progress, experimenting with new materials and designs. But it's also the gateway to electric vehicles going farther, renewable energy running cities, and our devices working smarter, not harder. Imagine a world where your phone charges in minutes and electric cars can drive for days. Then, there's radiation-engineered materials. Sounds intense, right? But tailoring materials with radiation is already pushing what's possible in space travel, medicine, and even making nuclear power safer. These innovations are opening doors to safer cancer treatments and more durable spacecraft. It's like giving ordinary matter a science fiction upgrade. We're talking about materials that can withstand extreme environments, or even repair themselves after damage. Now, where is all this heading? The possibilities are almost limitless, and the impact on our daily lives will be profound. Here's what excites me. The future isn't just about inventing new gadgets, it's about rethinking what materials can do. We're on the verge of a revolution in how we design and use the very building blocks of technology. Research is starting to blur the boundaries between electronics, biology, and chemistry. Scientists from different fields are teaming up to create things we've never seen before. That means we could see wearables monitoring your health in real time, alerting you to changes before you even notice them, batteries built into the fabric of your clothes, powering your devices as you move, or new materials that can survive the harshest places in the universe. Imagine sending robots to explore distant planets, or building habitats on Mars, all thanks to these breakthroughs. But, I'll be honest, the real breakthroughs are coming from corners of science that we can't even guess yet. The most exciting discoveries often start as wild ideas or unexpected results. It's the questions and experiments happening right now, the ones that aren't afraid to take risks, that'll shape the world you and I live in tomorrow. The future belongs to those who dare to experiment and push boundaries. So, what should you take away from all this? Stay curious, ask questions, never stop exploring, because every great discovery starts with a simple what if. Challenge what you think is possible. Push past the limits you see today, because tomorrow's breakthroughs depend on today's dreamers and doers. Because the future of science isn't just for researchers in labs, it's for anyone bold enough to wonder what if. You could be the one to spark the next big idea. Thanks for sticking with me on this deep dive into the frontiers of tomorrow's tech. I hope you're as inspired as I am by what's ahead. I'm always chasing the next discovery, and I hope you are too. The adventure of science never really ends, it just keeps getting more exciting. This is, for Science Salah Lotfy, signing off. Until the next big breakthrough, stay curious and keep exploring.